in this unit, we're going to look at something called regression, but really it's better to start sort of, I mean, the term is kind of a funny term, but so it's better to start with this notion of what we're trying to do. And the answer to that is we're trying to model these linear associations that we saw in the previous unit. So we have here actually a data set that is a bunch of students of mine who have told me what their shoe size was and how tall they were. So just a few of them. And when we look at this, we'd say, well, that looks, model, direction, form, and strength, right? It's positive, it's linear, and it's pretty strong. It's pretty strong. So that notion of a linearness is what we're after. So we could in some sense draw this line, this red line through that cloud of points, and show that it follows those points pretty well. And then what? Well, this idea of model means what we'll do is we'll, in some sense, get rid of that line. And by the way, we're going to look at a lot of equations of lines in here. So what I'm demonstrating here is the fact that you'd say, okay, the height is related to the shoe size by taking 51 and adding to that 1.8 times whatever the shoe size was. And that's this notion of the equation of that line, that particular line. So that would be great, in particular because I could get rid of those data points, and that line by itself somehow captures what was going on in with all those points. I mean, it still shows the positiveness. It shows the linearity, of course. Doesn't show the strength. That's true, but it does hold that information that 51 plus 1.8 times shoe size. That's that equation of that line, and that picture of the line goes with that equation. So, in some ways, I can simplify my my picture, getting rid of all the details of the particular data points. And that allows me to do a couple of things, like making predictions. So I could say, well, what if somebody came to me and they had, size 10 shoes? How tall would I guess they would be? What I'll do is I'll take their shoe size, I'll plug it in, that value 10, multiply that by 1.8, it gives me 18, add that to 51, and now I have a 69 inch. So I'd make a guess that a person with size 10 shoes would be 69 inches tall. Lo and behold, if I bring back the data, you notice that actually I did have exactly one person who had size 10 shoes and was 69 inches tall. So in some ways I've captured that. But of course you'd notice that it was a lucky choice. 10 was good. If I had picked 9 or one of the other ones, I wouldn't maybe necessarily been exact, but I've been close. I would have been close. So that line, that red line, really does capture what's going on and the complexity of that cloud of points. The question next is, well, I picked this line. I kind of eyeballed it. I put the line down there, and picked numbers 51 and 1.8 to make it look pretty good. But was that really the best line? Now, that gets to the first big question: what the heck is best? What do I mean by best? But before I do that, I want to review the notion of what the equation of a line looks like. So this notion that in high school algebra you learned y equals mx plus b, m being the slope and b being the intercept. But in statistics we actually take a little bit different tack, and there's a reason for that, but it's kind of more advanced in a later statistics class. It becomes necessary to use different forms, and so instead we usually write a y hat equals b0 plus b1x. The hat on the y indicates, this little circumflex indicates that it's an estimate. Okay, so it's kind of a guess at Think of this being guessing the height from the shoe size. I'm taking a guess of that height. So the hat indicates to a statistician we have an estimate or guess. And then the intercept is B0. We write that first. And then we add to that B1, which is the slope, times X. And we actually go further. I don't know if you noticed on the previous slide that I wrote, instead of Y and X, I actually wrote the variable names, which shoe size and height for X and Y. So I just want to make that clear. B0 and B1 are my slope and intercept still. It's just I write them in a funny way. So I should say B1 is the slope and B0 is the intercept. And finding a line is really finding the B0 and the B1. So each line corresponds to a B0 and B1, and each B1 and B0 correspond to a line, a unique line. So when I say find a line, I don't mean doing it geometrically necessarily, but rather finding these two coefficients, these two values. So the getting back to the question is what is best, and what I can do is I can sort of say, well, that line is supposed to make good predictions of people's heights, and I have some people here, these data points that actually I have heights recorded for and shoe sizes. So I can look at what statisticians call residuals. So let's focus in. I have one point. I don't know if you noticed right up here. It's in red. And that's one person that had entered the survey, and I can actually read off that one person. It looks like he was 71 inches, and he was size 10.5 shoes. So I can sort of say, well, what would I have guessed him to be? So here's how that works. I'll take his point, and you can you can do geometrically. I can take that point, and I can sort of drop down to the x-axis to show that he's a 10.5 shoe size. Then forget about him for a minute. Forget about that particular person. Let's guess, using that 10.5 shoe size, how tall he would be. In order to do that, I start at the bottom at 10.5, go up to the line, and then go over. And so it turns out, and it is equivalent to writing putting 10.5 in that equation, and what I would get is 69.9. And then I will also look at him. So in other words, I want to look at his actual height. He actually said 72 inches. And so that difference is what a statistician calls a residual. I get him to be 2.1. Okay, so in some ways, he is 2.1 inches taller than what I predicted him to be. Okay, and I drew the residual as a little red line over here on the y-axis to show the difference between 69.9 and 72, but it actually is convenient to draw it right at that point. So that point, that red line actually goes from the point down to the line. So I travel in a vertical direction. Try that again. Say try this person right here, and I'll drop down right to the x-axis, go back up to the line, over, and so his predicted height was 70.8, but the actual height of that person was 69 inches. And so I'm going to take the difference, and I get negative 1.8. And that negative is important because what that tells me is that that he or she was actually shorter than what the line would have predicted that person to be, right? And again, I get a move that red line over to that person. Just going a little bit faster, I have another person here, 71 inches, and that actually is right there. It's kind of hard to see, but it's behind that red line. That there was a person there who was 71 inches tall. But I would have predicted him to be also 69.9 because they indeed had 10.5 size feet, and all 10.5 size feet people, I put the 10.5 in the equation, I get 69.9. So that's my guess for that group of people. So they had a residual of 1.1, and then let's see, 70 inches. Oh, again, sort of underneath that red line. This is by accident, by the way. I'm sorry. But I would have predicted them to be 70.8, and that means they're below the line negative 0.8. And I can do that for all these lines. And the bars, some of them are overlapping, like this one. There's actually 3 red bars. They come down here, but 1 bar to each of the points. There is also a notion that these residuals, and I said the sign was important because the positive residuals are those points that are above the line, and the negative residuals are below the line. So, and another way to think of that is the positive residual ones, the ones above the line, are taller than what I would have expected based on the line, and those with negative residuals are ones that are people that are shorter than I would have expected based on the line. So the formula I'm following here is residual is equal to actual minus predicted, and I put an I down here because it's for each person. Each person in this data set has their own residual. So there, if there's 50 people in the data set, I have 50 residuals, some positive, some negative. And these residuals somehow contain the goodness of this line. I want a line that has small residuals. And we'll deal with that in a second. Just to do symbolically, what we'll often do is write actual as yi, so that's the actual person's height. And remember the hat, I told you the hat meant predicted or estimated. So this is their estimated height. So the actual height minus the estimated height, where y in this case is height. Another way to write that, because y hat, remember, is what I get from the line, is b0 plus b1 times xi. So I take the line that I generated and take the shoe size that goes with that and compute the predicted height, and I subtract that from the actual height, and that gives me the residual. So which is best? And of course what I want is one with small residuals. So that one looks pretty good. I mean, this line right here looks pretty good because it goes along with the points. But what's the smallest one? Because maybe that also sort of goes along with the points. It's not very clear if that's actually better. That definitely is wrong, right? I mean, it's clearly wrong because the points are positively associated. This is not following that positive association. It's a negative association. So they can't even be. That can't be, I hope, a good fit. That again is not so hot. Okay, it's flatlined. But that's not the way the data is going. It's positive. It goes up from left to right. So here are 2 of those lines that I had shown. Which one has the smallest residuals? Right. That's what I really want. Now, one thought is, well, if I have 50 data points, I have 50 residuals. How do I find the smallest in general? And what I want to do is something like an average. The problem with that is that this when I add up the residuals. So remember the sign sigma is add up. It's adding up y minus yi hat. That's the formula for the residuals. I could add them up, but in some cases, I get very small sums of residuals. So in other words, this one right here, this line right here, think of what the residuals look like. Remember, what I got to do is put red lines up to each of those points. And when I add up these residuals, what's going to happen? Well, I have a small residual here, but it's negative, remember. And I have a small residual here that's positive, so there's going to be some cancellation. And this negative residual will cancel with that negative residual, and maybe even a little bit of that one. And that negative residual will cancel with that positive residual. Sorry, these are positive residuals over here. And so forth and so on. So I'll have lots of cancellations because the negatives and the positive will cancel each other out. So this terrible line, remember, it doesn't even follow the points. it goes down from left to right, might actually have a very small sum of residuals. So what am I going to do? Does this sound familiar? You might remember that we had a similar problem when we were looking at the standard deviation. And one idea would be to perhaps get rid of the sign, make all the negatives positive, right, by using what's the absolute values. But the absolute values are not very good. They're not clean mathematically. They make life difficult. So of course, what do? We square the residuals. Remember, we did this with the standard deviation. That squaring removes the sign, right? Because two negatives are a positive, right? Or I should say, a negative squared is positive. And so what we'll do is we'll look for the line. Hopefully there's one. The line with the smallest sum of squared residuals. That's what we'll call this, because it's the sum of the squared. Remember, and this is the residuals. Okay, and we actually don't use residuals in this case. We actually call them errors. So we'll say this is the SSE, the sum of squared errors. Okay, so we've got that. What we want to do is we want to go out and try some lines. Try a line, compute its SSE. Then we'll go find another line. All right, try another line. Compute its SSE by computing the residuals, squaring them, and then adding them all up. And whichever of those two lines has the smaller SSE, that's the one we'll keep. And we'll go look for another line, hopefully something with a smaller SSE, and so forth and so on. So here's some examples. Right, so if I put 50 here and 1.85, so 50 is the intercept, 1.85 is the slope. I went and used the computer, of course, and I computed the SSE for that particular line, 88.754. Okay, so that's fitting pretty well. What about this one? Remember, this is the one that we used at the beginning, right? It has an SSE of 77.09, which is actually smaller. So, okay, this is the better of the two lines, right? Because it has the smaller SSE. And what about this line? Oh, well, that's terrible. And notice its SSE is huge. Indeed, not very promising. And what about this one? 51 plus 1.75, right? So a little bit. Oh, that SSE is a little bit bigger than the other ones. So maybe this isn't as good as one of the other ones I found. So I could continue to do this, right? I mean, it's going to get really ridiculous though. Trying every possible slope and intercept, and trying to find the one with the smallest SSE. But it turns out that I don't have to do that. With a little bit of math, it's more complicated than we want to get into. But with a little bit of math, we can actually find the line that has the smallest SSE without doing a whole lot of work. All right. So what is that? Well, here's the formulas. The slope is simply the correlation. Remember, that's what little r is. Times the standard deviation of the y's. So to compute this, take the heights of all 50 people, compute the standard deviation of those heights. And then S sub x here is the standard deviation of the shoe sizes. Okay, so I take those shoe sizes and I compute the standard deviation of the shoe sizes. So I take the ratio of those two standard deviations, multiply by the correlation, and that is my slope. And that slope is the slope of the line of best fit. But of course, I also have to supply an intercept. But the intercept is, remember what the bar is above the y. That's the average or mean, right? So that's the mean of the y's, the mean of the x's. Take the mean of the y, subtract the b1 that you computed in the first step, times the average of the x's, the mean of the x's, and that will give you the intercept you need. Okay, so those two numbers, and notice it depends on the standard deviations, the correlation, and the two means. I can compute, if just knowing those five quantities, I can compute the slope and the slope and the intercept of the best line. Okay, the absolutely best line. Nobody else beats it, and actually nobody even ties it. Okay, so it's fair to call this the least squares line. That's why I emphasize the in the title here. It is there is none better. So when I go and I get my data, I've got those people with their shoe sizes, and the average was 9.567. I took their height average of their heights at 68.383. I computed the standard deviation of the shoe sizes is 2.016, and the standard deviation of the heights, which is 4.262, and of course the correlation. And notice that's a nice 0.928, pretty strong correlation. And then I just simply plug that in to these two formulas, and I get 49.615 is the correct height, correct intercept, sorry, and the correct slope is 1.962. So, and the SSE of that line, that best line, is 73.203. So, indeed, there is no other line that has a smaller SSE. This is the line of best fit.